Yeah, and you gotta record the
We were just talking
Discord
about, like,
call. So
How do I go about that?
Artem's issue.
I'm not entirely
That's all
sure.
I know.
I think you can just click on the event thing and then just record your entire screen, and that should be fine. Because I have the slides pulled up on my end.
Yeah, I knew my Instagram.
Oh, the event thing? What's that?
Okay, so just click on event
Oh, yeah.
and then just record your entire screen. And
Okay, watch the stream. There you go.
Yep, and that works. You shouldn't need to necessarily watch the stream. It should be, but it doesn't matter.
Okay.
You also want to turn off non-video participants, so just 3 dots.
Yep.
There we go. And then it's
Sick.
just the cam and cam. Alright, perfect.
Yeah.
And OBS is recording, right?
Yes.
Yeah, and now they
Alright,
just talk about
I can.
Yeah.
Yes.
Alright,
GitHub and
perfect.
some other shit.
Alright, then yeah, we're good on the recording setup.
Works.
We have people here. We're still waiting on Constantine and Dan. They should be here soon. And then we can start. Oh, there we go.
There you go.
Hello.
Did they go?
Yes. And I think
Holy.
the car is going to be brought closer.
This is like
Yeah.
a lot of people.
Just making sure people
Yeah.
actually survive.
We got people in the VC as well. It looks pretty good.
Yeah.
This is like the highest attendance.
Yeah, I know.
Yeah. Weird.
We advertised for the first time, I think.
I know.
Yeah.
This is what happens when you come to GDW with an announcement.
Right?
Yeah.
Look at that.
Also the fact that we have a good session time.
Yeah.
We gotta bring him in.
But yes,
He,
all right.
he has inner Tall Howard.
Truly.
Constantine can't stop winning. There you go.
Truly. All right. I guess since everyone is here, we can just get started. Yep. That's okay. That should be fine. All right. So yeah. Welcome to our procedural generation session, everyone. Yes. So for the intro, so what we're going to be doing during this session is we're going to be exploring 2 general approaches for procedural generation. One is wave function collapse, and another is noise displacement. So using Perlin noise to displace some terrain, to get some terrain going. And we'll be exploring pros and cons of both these techniques and why you should use them. All right, so first let's start with wave function collapse.
All right.
Yep, but first I gotta explain one thing. Yeah. No, don't worry. We'll get to your part soon. That's actually the next slide, I think. But
I'm too excited.
yes, so
This is my bread and butter.
first, wave function collapse. What is it? So it's effectively a rules-based algorithm. So you define some rules, and then based off of those rules, it'll generate something for you, and that's essentially how it works. And these rules can be things like adjacency. So you can say X tile should be next to X tile, or Y tile needs to be next to Y tile. You can also define probabilities. You can say X tile has a 50% chance of appearing, right? And you can also do something, you can also make it so that the algorithm, instead of having to define the rules yourself, you can make it so you build a small model, and then from that model, the algorithm sort of learns the rules, quote unquote. And if you do that, then you can also have another parameter, which is similarity. So you can change how similar the output will be to the input model you give it. And we'll be going over all of that later. And also, just a small technical note for anyone that knows, that's done research on this. We will be conflating 2 different algorithms. So really, there's wave function collapse does not do the learning thing. That comes from model synthesis. But we'll sort of be combining these 2 concepts together because they're very similar algorithms at the end of the day. But yes, so yeah, first off, I want to start off by showcasing what wave function collapse can do before we get into sort of how it works, which Dan will be explaining. So first, let me pull up this. So one thing wave function collapse can do for you is you can procedurally generate in real time sort of
Lab monitor?
yeah, is it doing good? Yeah. All right, so let me just do that. Yeah, so one good thing about wave function collapse is because it's a procedural generation algorithm that you can use to generate levels, what you can do is you can generate in real time. So this is a demo of an infinite city that generates as you walk through it. So this is something that you couldn't do with sort of an artist, right? Because you couldn't build a level this intricate and this big, right? and it also generates around you as well. I believe at the end of the video, there's sort of a fly through. So yeah, they're sort of flying through the city, and they're not. Oh, it's not it. There we go. They're flying through the city, and you can see it generate in real time, right? So yeah, so one of the things that's possible through wave function collapse. And another showcase is you can also just generate static levels that don't generate in real time. So this is a famous set called Escheresque. So it's notoriously complex. You can see there's a lot of sort of parts to it. There's a lot of pieces and little details. This is something wave function collapse is pretty good at, because as an artist, it would be really difficult to build this out yourself, right? Even if you had all these tiles and you had to put them all together, right? But the algorithm can do it for you within a matter of seconds, right? And now, let's hear Dan explain how the algorithm works. Let me pull up the presentation for that. Should be in a new tab. No, it's the wrong tab. There we go. I need to share it. There we go. All right. There we go. Take it away, Dan.
You could have asked. I could have appended it to the other one, but it's okay.
Yes. No, it's fine. It's fine. It's fine.
Can I just have the mouse, because there are like 50 slides I have to get through.
Yes. Here you go.
Can I hold on to?
Yeah. It's
No. Can I grab my mouse just quickly? It'll be easier for me to hold on to it instead of.
Yeah. I wonder if you could touch the screen. No.
I am so excited. I am shaking because this is what I do. This is what I love.
Here you can.
Is it this one?
Yep. You just plug it in there.
There we go. And all right, procedural generation with wave function collapse. Turn it on. There we go. All right. Can you quickly play the video?
Yes.
This is going to be an explanation of the algorithm, the specific implementation that we used in Starlight, our game. Click no, that's malware.
What was on that mouse?
This is just a visualization of how the algorithm actually works in scene.
Let me skip ahead to the.
Yeah, you can skip ahead. Right now, every single blue tile, I'm not sure if it's easy to see in the far back, blue on blue, but the way algorithm works is it goes tile by tile, checking to see if tiles conflict within a certain array, and just sort of removes tiles procedurally as the level generates, placing them down one by one until finally you get a finished room. We can just sort of, click
Yeah.
off of that.
Yeah, I'll.
That's the wrong
one. No,
laptop.
it's yeah.
I'm sorry.
It's okay.
What is wave function collapse? This is the definition that Google gives you. It is not important. It doesn't matter, right? Here's my step to absolute development hell, because that is what our generator looked like majority of the first semester. To start off with, we're going to start off with just a 2D representation of wave function collapse. Tiles. It is the entirety of how wave function works. It is all defined on rules, tiles, fitting them together, right? The way we developed it is using a key socket system, identifying 2 IDs per face of each tile. Oops, I went too far. Oh, can you go back one?
Yes.
Is
that it?
One more, please.
There we go.
Yeah, there we go. Yeah. 2 keys. Why do we need 2 keys? So each face associated with it. I'm sorry, I'm not allowed to touch the screen, or
No, you are. You are.
I'm allowed. Okay, just on accident. Each face has a key and a socket associated with it. You might ask, why not use just one key, one ID? In certain cases, you want to identify specific interactions with each tile. Let's say staircases, right? It doesn't make sense to have a staircase that goes down and then immediately back up, right? Kind of creating like this zigzag pattern, right? Using 2 keys or 2 IDs, we can pair them together to create specific combinations that allow us to control which tiles fit together and which ones don't. Again, defining the rules. So let's start. Let's place a tile. Hey, tile. Now what? Let's look at the grid, right? We need to visualize what this actually looks like so we can understand what goes into a grid. All right, here's a grid slot. What is it? It is effectively an array or a list, depending on if you're using Unity or Unreal. Doesn't matter. It contains every single possible tile that can potentially spawn in that grid slot, right? And I mean every single tile that's possible, variations included. So this is what it really looks like. You have your spawn tile and every single possible tile possibly surround it. Next, let's look to one side, right? We have our generator tile and our slot. Right now, what we want to do is remove any tiles that don't fit with this one face. So looking here, I'm not sure if it's easy for people in the back to see, but we want to remove any tile that doesn't have a door connecting to the left tile here, right? And so how do we do that? Simple for each loop, right? For each tile in this slot, compare it to that door. If it doesn't fit, remove it. Easy enough, right? If it does fit, keep it, leave it. We're going to move on, right? Until we get something like this, right? We removed all the tiles that don't fit. Any one of these tiles, if they were to spawn, will fit with that tile perfectly. All right, one more step. We look to its neighbors, right? So now that we have something like this, obviously, not all of these slots will have tiles that fit with the possibilities of this tile. So what do we do? Do it again. It's another for each loop within a for each loop. For each tile, loopception. There's a joke on another slide. Yeah.
Oh,
Not even.
sorry.
No, you ruined my joke, but I'm
I
more than
stole your
happy.
joke, man.
No, you're learning. You got it, right? For each tile, we want to compare each tile in this one to see if any of these fit. If there's a tile in this slot that cannot fit with any tile in the slot that we're checking, we have to remove it, right? Loopception. Thank you so much. And we just keep going. It's a recursive algorithm, so one tile to the next tile to the next tile to the next tile, and we keep going until chain ends, right? When does it end? Yeah, go ahead.
Sorry, one thing that is bugging my mind right now, wouldn't this be real, like, CPU heavy? If you're, like, the bigger, like,
Yeah.
you grow, like, if you have, like, a 4x4, and then you have a 5x5, you're, like, slowly growing up, wouldn't be more and more heavy because you have to do this for over and over and over again?
Yes. I'll get to that later. There is a small bit, yeah,
Thank you.
but good question. When does it stop? When we stop updating a tile, right? So if we do not remove a single tile from this slot, nothing's changed. We know for a fact that any future tiles aren't going to change either, right? So why keep checking? It's done, right? So, oh, and while we're checking, this is important to realize. Hello. Let you in here. What happens when we only have one tile left? We're checking, and suddenly we only have one tile left in a slot. Place it. That simple, right? It exists. Nice. So once we're done checking, once we've removed all the tiles that conflict with the tile we placed, we're left with something like this. And now we place another tile. Ideally, we want to place it where there are the fewest possible options. That way we can, I want to say for stability,
Yeah, I believe it.
probability-wise, like if you try placing a tile up here, it's likely something will conflict. So the reason we do it, place it here, least likely something's not going to go wrong. Ideally, if you've defined your tiles correctly, it should be fine. And we repeat this until, yippee, we place enough tiles to create a level, right? So, final notes about this algorithm. It doesn't have to be squares. It can be cubes, it can be triangles, anything that tiles, right? So long as you can define each side and track which, like the coordinate slot of where each tile is, you can make this work, right? Get weird with it. You can have weird octagonal tiles so long as you know and understand which faces correspond to which tile. If you can read that, define how that works, you can get wave function types to do something with this sort of tile set. Another important thing, developer and designer tools. This is something really important. Why are you making procedural generation in the first place? It's because you don't want to do it. Make the computer do it for you, right? Make it as easy as possible for yourself, right? Look at these guys. Remember them? The computer can do that for you. You don't have to rotate them yourself manually, add them all. You just have to create 3 tiles and let the computer do the rest. What's that? 9 times 4? 36. Out of 3 tiles. This is an example that we have from our game. This is how I developed it in Unreal Engine. This is our implementation. It is just an actor class that I created as a child. It's a copy-paste for my team, which didn't use it. Blaming you. Kidding. But I tried making it as easy as possible to make tiles for them, right? So here's a big blow-up of what it looks like inside the editor. Top right, you have your data values, so your tile variations. So if there are different types of tiles that fit within the same key, right? So same door location, same floor location, same wall. If you have variations on that same tile, you can place them in here, right? Going down here, tile ports. So it is named a little bit differently here in this screenshot than it is inside the presentation, but we have the key and socket IDs, so one for each side. You can kind of see how they all appear down and below and a little bit to the left. Fill them out right here. That's defined as your keys and ports, right? Really easy. You have your probability. So if you wanted, like mentioned before, if you want to make a tile more common than others, so for example, walls, doors, floors. If you want larger rooms, you would probably make open spaces more common than walls, right? And other than that, yeah. Here's the optimization thing. Here's what I didn't do. Because it's all in. Hello, welcome. Do you want to come in? Anything? No? Okay.
Yes. Have a seat, dude.
Have a seat, yeah, go ahead. Do everything in C++.
Yes.
Blueprints is very limiting.
Yes.
It is intended by namesake to be a blueprint. It is meant to prototype. I ran into difficulties trying to figure out a way to multi-thread it. I didn't find a way, and I ran out of time. So we ended up with, if you remember the video, it was slowly snaking around, checking each tile, tile by tile. Very slow.
Yeah.
And that was only like, what, 30 by 30 by 30, I think? Something like that, yeah. Make it in C++. You can take advantage of the GPU, because it's a for each loop. It's a recursive operation that's happening over and over. It's recursive. It's the same thing. Multi-thread it, multitask it. Get like thousands of operations going a second with the GPU. Like, it'll go much faster than what I did, because mine was single core bound. That thing was slow.
Get an AMD Epic server CPU.
No, he's on something. Look. All right, and do as I say, not as I do. This is all right. This is generally well commented. Like, you have your intro, like on begin play. You have your debug tile set, which I think is down here. You have your if statement to tell you if. Right, generally well commented. You can read this. Right, most of you, if you were given the opportunity, would look at this and say, "Okay, I can see where this is going." What about this? Not so bad.
Well, they're overlapping.
Yeah, right here.
Where's the
Look at that.
spaghetti? Where's the real spaghetti, man?
Real? No, you haven't seen nothing yet.
No, I have worked with Unreal. I know the spaghetti gets. Where is it? I want to.
You want to get to it? All right, I'll tell you right now. This is for our loading bar.
Oh no.
This, too blurry. I can't read that. I don't know what that is for. I cannot tell you for the life of me. This, I have no hope telling you.
No.
You didn't find mine, did you?
Huh?
You didn't find mine, did you?
No, this is mine. This is only mine.
I'm saying,
Okay.
This is a roast B section, not roast you. I wouldn't do that to you. That is it. Do as I say, not as I do. Comment your code. Otherwise, you end up with that, and it makes your life so much harder. The whole point of ProcJet is to make life easy for you.
Yeah.
And that did not make my life easy. That's me. I'm done. That's wave function collapse in a nutshell.
Yes.
If you want to move on, go for it.
Yes, thank you, Dan. Thank you.
Here's my announcer. If I could just yoink that little guy from you.
Thank you. And let me
you.
switch on over.
We'll just go to
Yeah. Hopefully you didn't give me anything too bad.
Logitech options plus.
Yeah.
Rather than kind
I have moved on from Logitech.
All right. So that was it for the showcase segment with Dan. Thank you for that. All right. So one thing to cover with wave function collapse is that it can fail. So you need to prevent that from happening, because you just won't have a level if it just fails. So there are a few ways you could do this. One is you could just restart the generation from scratch. So the idea is you iterate over all tiles and you collapse one tile if it has, if it meets certain conditions, right? But what can happen is you could run out of tiles to collapse in the entire thing, right? You could remove all possibilities from every tile array. And then what happens is when that happens, you can just restart the entire thing from scratch, right? But of course, that is very performance intensive because you're restarting all this work that you did. That might not necessarily be bad. So a better way of doing it would be to back up one step. So you could just undo what you just did last time and restart generation again. Because of the way, because of how wave function collapse uses randomness when there's multiple options in one tile, it'll give you a different result, right, if you back up. And another thing you can do is implement an algorithm called generation in blocks. This is another thing from model synthesis. But yeah, and also the first two approaches are really just band-aid solutions. They won't work when it comes to generating large tile sets. We're talking like hundreds by 100, like 100 by 100 by 100, right? So if you want to generate a really large level with a really complex tile set like Escher-esque that we saw before, so let me just bring that up. If you want to generate something like this, you need to implement generation in blocks because otherwise it's just not going to reliably do it. So yeah. Let's look at generation in blocks. So another thing about generation in blocks is you can also parallelize it. So that's a good way to get performance back. So essentially, this is really easy. All you do is you split up your level into tiles, essentially. So instead of generating 30 by 30, you split that up into maybe 4 by 4 sections. And you generate each 4 by 4 once, basically. And what you're doing is you're reducing the size that you had to generate at a given time. So this reduces the chances of failure. Because the way it works is as your level increases in size, the chance of failure increases as well. So if you just make the level really small, then you won't have to deal with that. And this also has a really simple way of handling failure. You can just regenerate the block that failed. So if you have a block that fails to generate or a tile that fails to generate, you can just discard all the data that you did for that and just restart it, right? And this way you're not doing too much work because your tiles are going to be pretty small to begin with. So yeah, it's a pretty nice way of handling failure. And you can also parallelize this pretty easily as well because what you can do is, let's see, I should probably draw it out to fully explain it. Is this gonna let me? Okay, whatever. It's okay. I have some resources at the end that you can look at that explain this better. So yeah, essentially, what happens is you generate each tile in this grid, and you can generate all the tiles in parallel. But you need there to be an offset because what's going to happen is, because of the way wave function collapse spreads adjacency data, you need to, so you need to generate the entire level once with tiles, and then you need to shift each tile one block over, then generate again. So you have to do that multiple times to get the corners correct, the edges of the tiles correct. I'm not doing a good job explaining it because I do not have a diagram. It'd be better if I drew a picture. It'd be way easier to understand. But yeah, there's resources. There's a resources section at the end that you can look at that'll explain how to implement that. And really, you only need this if you have a lot of tiles that you want to generate. So yeah. And another thing you can do to sort of make your life easier is you can infer the rules from an example. So instead of defining the rules manually yourself, so you can say like a stair tile has to be next to this tile or that tile, right? Instead of doing that manually yourself, you can have the algorithm infer the rules based off of a model that you build. And the way that works is actually pretty straightforward. All you do is just keep track of each tile that's in the input, which is very easy to do if you have like a 2D thing. If you have a 3D thing, you can just do a collision check, right? Just have a 3D grid of cubes and just do a collision check and then check the name, right? If the name is already, and then you can add the name to an array, right? And this way you know that's one tile that you have, right? And you can just go over everything in the grid and just count up the number of unique tiles you have. And one thing you can do is you can also figure out which tiles neighbor which other tiles through this way. You can just check one tile, check to the left, right, up, down, forwards, backwards, and record what its neighbors are, and store that all in sort of a data structure that you can use, and that'll be the rules generated for you. And this way, when you infer the rules, you don't have to configure them manually, which can be incredibly tedious when you have a lot of tiles. Really, I would always recommend inferring the rules. The original wave function collapse algorithm has this built in, so I would highly recommend that. And you can also sort of generate the rules based off of some other data, but it's not very general. Oh yeah, also, by edge data here, what I mean is you can, again, this is difficult to explain with the picture, but you can basically, like, I saw this one algorithm for generating terrain with wave function collapse, and the way it worked is the guy took screenshots of the tiles in Blender, and he used some sort of algorithm to determine where the empty space was, and that was sort of the key, right? The sort of the key and socket analogy, that was the key, right? So if another thing had the same empty space area and looked the same way, then it would fit together, right? And this way you don't need to generate any rules at all, and it's all done based off of just edge data alone. But that is something that I've only really seen once, and it's not very generalizable, right? Because you could imagine that not working out for things where you don't have terrain. But it's also very convenient, because then you don't even need to build a model. So yeah, that's something to keep in mind. There might be a better way of generating rules for your specific use case. And also, I think, yeah, there's another thing that you can do. So I mentioned similarity a while back. The way similarity works is it uses something called the overlapping tile model. This is also described in the original implementation of wave function collapse. But the idea is, with a simple tile model, what we do is we check every single tile in the input, right? And we look at all the neighbors. And then from that, we get our adjacency data. But what you could do instead is you could do this in blocks, right? So you can slide a block over your input, figure out what's in the block and what neighbors the block, and then from that you can generate like that. You can get the adjacency rules like that. And the idea is how big of a block you use will determine how similar the output is to the input, right? So if you have a block in the input that is the same size as the input, right? And then you try to generate an output with it, it'll only generate the input, right? Because that's all it knows. It knows that one tile, and that's the entire input, right? So yeah, essentially you can get similarity that way. And yeah, and also there's some pros and cons. So yeah, the pros are you can generate a huge level from a small example, or from manually defined rules if you want, or from edge data or whatever you prefer. And you can also have different content per run or per player, and you can have things generated in real time as well. And it also could be a good starting point for a proper level design. Maybe you want to start with sort of procedural generation, and then you want to have an artist come in there, tweak things, right? So that could be pretty good. But the cons are, with any procedural generation technique, is you give up control, right? Because at the end of the day, the algorithm is generating stuff for you. You're not doing it, so you're going to give up some artistic control, right? And it only works for generating things that can be broken down into tiles. So things like cities, things that constantly have a lot of repeating elements, it works very well for. But not for something like terrain. Like if you want smooth terrain, like mountains, hills, valleys, rivers, stuff like that, you can't really use this algorithm. It can generate some terrain, but it's really blocky because of the way it works on a grid. So yeah. And here are some sources as well. We'll be putting up this we'll be uploading the slides to our Discord so you can see it there. But yeah, you can go through these references, and yeah. And now, let's move on to our second algorithm, noise displacement.
Oh,
Take it away,
who's
Ethan.
calling me? That's convenient timing.
that is
Get
very
out of here,
unfortunate.
So, noise displacement. We're really reeling in the scope in comparison to wave function collapse, because this is just Minecraft generation.
Yeah.
And it's a perfect complement, because this can do what wave function collapse can't.
Yeah, exactly. So basically, noise displacement is a method used in procedural generation. Basically, you can just take a noise map, so you generate it, and then you will just sample the pixel data in order to get whatever data you want. So in today's example, it will be like height map, but you could use it for a lot of different things, like texture generation, things like that. Particle noise, whole lack of other applications. Anyways, next slide.
Actually, first, could you tell us a bit more about what noise is? Is it like sound?
No, it's not sound. Basically, it is just a 2D texture that you will generate with a bunch of black and white data, and black being 0 and white being 1, and then you just sample the pixels so it will fall anywhere between 0 and 1, and then from there you can translate that data into something else.
Yes.
So, noise functions are used to create natural-looking variations in, again, terrain generation, texture mapping. You could use it for object placement. I've seen it used for particle displacement as well. And your main values that you'll be using for this are amplitude, frequency, and octaves. So, amplitude is the strength of the displacement. The frequency is the scale of the pattern, so how big the, let's say for Perlin noise, it's all dots, how big the dots are. And then octaves is just layers of noise. So imagine you have one texture, but if you have 4 octaves, that's actually 4 textures that you will be sampling from. So that is just more complexity and, I guess, finer detail. Noise displacement generates organic, non-repetitive patterns, making it ideal for terrain, texture. Yeah, okay, we've already covered this, but this is the pros of it. You can use it for just generating, I guess, finer detail things than you could get with wave function collapse, I guess. You can also adjust the parameters like amplitude and frequency so you can really fine-tune what you are generating. And yeah, so next slide. So again, this is an example of just a variation that you can get. Here is a Minecraft world with like regular amplitude, regular amounts. This is an amplified Minecraft world. You can see it's the same algorithm, but just the scale of the amplitude is bigger, so it generates 2 completely different things. And then the cons of using noise for generation. Fine-tuning exact results can be challenging. For the demo that I was developing for today, I was just tweaking the values a lot, and there was a whole lack of variation, and I couldn't get it to look right for a little bit. So it doesn't guarantee precise outcomes, and the small changes in parameters can drastically alter the results, so it really is just about fine-tuning. While noise creates random organic patterns, it might not always align with artistic design. So again, you really have to fine-tune those parameters in order to get it to look how you want it to look. And then additionally, the same noise patterns can repeat across large areas, which can create unnatural or boring results, but that's where the octaves come into play. That can create more variation. So yeah. And then, so No Man's Sky, this is really funny because they just released an update that completely overhauled their terrain generation today. But they have notoriously repetitive planets. So yeah, that's another con. So why should you use noise displacement? Noise functions naturally produce non-repetitive varied patterns, making them ideal for generating realistic landscapes, terrain, and textures. Instead of crafting every detail by hand, noise displacement allows for the rapid creation of complex structures like terrain or cities, using just a few simple parameters, so it's very time efficient. And by adjusting the parameters like frequency and amplitude, users can find the perfect balance between randomness and control, enabling them to create generated controlled chaos, which feels natural and unpredictable at the same time. So, demo. Hopefully I have it. Yeah, so...
Alright, I guess you gotta share your screen.
Oh, okay.
And then I'll just stop sharing my screen.
Yep.
There you go.
Here, will that work?
Yep,
Yes.
that looks good.
So as you can see here, you can define just...
And,
is it working?
I need
Oh,
to actually watch your thing so it shows up on the thing. There you go.
Okay, so as you can see here, you have basically just grid scale. That's how big your grid will be. And then you have the amplitude, which I've set it to 1, so we're going to have more like normal looking terrain generation. You have your frequency, again, that's the size, and then just your octaves. And then I also added terrain carving, so you're going to see a mix of both 2D Perlin noise and 3D Perlin noise, where 2D will be just for the height map of the terrain, and then 3D will actually carve out shapes from the terrain. And then you have a seed, which is another concept used very frequently in random generation, which the seed basically, you change the seed, you just change how the noise texture looks. That's pretty much it. And then if we run this, I just implemented the seed before class, so hopefully it doesn't break everything. It's gonna generate, yeah. So, it's Minecraft. I need a mouse,
Oh, I know.
actually,
You can use mine.
so that I could hover around. Thank you. So my implementation algorithm-wise, is optimized. However, what I'm doing is very bad
Yes.
because I'm just instantiating a lot of blocks because I didn't feel like actually like.
Culling the
Culling the back faces and actually connecting them because time. So there's a lot of draw calls happening, which is not good. But basically, you have Cave Game, which is very early Minecraft, and if you were to, let's say, change the seed to this and change the frequency, let's lower the octaves. Let's see what this does. Did it even generate anything? Oh yeah.
Yep.
So yeah, as you can see, that doesn't look very good. So that's why it's important to play with your values. What did I even have it at before? 4, 1. So yeah, and then this is a very
You guys
basic.
have questions or?
Oh yeah.
Why instantiate cubes instead of just like placing points and using one mesh regular?
Time.
But it's still one function call.
I know.
Yeah.
But basically, I was just like, okay, I want green cube to generate on the surface, and I want gray cube to generate underneath. It was just for the sake of the demo.
Oh, fair enough.
So this is.
Oh, another question.
Oh, another
From
question.
Dan.
Yes.
Not necessarily a question, but I do have my own implementation of exactly that if you want me to come back up there later and show you.
Oh, that'd be cool. Yeah.
I'm sure you
It's
have the
literally-
intersection.
I have one for terrain and one for tiles.
Nice.
Except in 2D / isometric 3D.
It's 3D, but we're kind of making it look 2D.
Hmm.
No, I'm talking about like the older one.
Oh, the older one.
I made
Also,
two
you're not
versions.
sharing
I
that, by the
have-
way.
Oh, I'm not sharing that?
Yeah, you just want to share.
I have
that.
screenshots of the older one.
My bad. Sorry.
We've been doing this for a few years.
Yes.
By we, I mean he has.
All right, so
Like
yeah.
bread and butter.
Now let's look at
What
some
I'm
code.
working on.
Let's look at some code.
Why is with that wide ID
Yeah,
He likes light mode.
I like light mode.
I'm used to it.
Yeah,
I've
You
called
scare
them
me
psycho
as an individual.
I downloaded Visual
I'm
Studio and I'm like, that's default. I like it. Okay, so let's roll with it. So basically, the first thing you're going to do is you're going to want to define your grid. So you just have a bunch of for loops for your grid. And then what's happening here? Basically, you're going to sample the height data for the 2D Perlin noise, which if we come down here, this is all it is. This is Perlin noise 2D. Basically, mathf, and then you just do your x and your z because you don't want to factor y into it because it's just like height data. And then, so for here, you just find your height. So you just get the terrain height, and then you feed the height into what you're instantiating. So if you're above a certain, or yeah, if you're equal to the height, you are the grass block, and then if you're below it, you are just going to be a stone block. And then for the next part, so you've got your height map, and you've kind of figured out where everything's going to go. Then you can do cave carving. So if now you can check 3D Perlin noise, which is the same thing as 2D Perlin noise, but now you have to do it for X, Y, and Z. But then you you have to figure out X, Y, Y, Z, and then X, Z. So you figure out all those combinations. Then you figure out their inverses so that you can get a 3D point in space. So then all you're checking here now is if you are greater or equal to the cave threshold, then you can generate the blocks, but then if you're not, don't generate anything there, so that can carve the cave shapes through the terrain. And that's pretty much it. It's a very simple implementation. It's only 120 lines of code. Most of it is probably comments. But yeah, Minecraft generation.
Well, yeah, I mean that's
in a
amazing.
nutshell.
Yeah, you can share Minecraft again.
Oh yeah.
Yep. I mean, yeah, it's pretty amazing. From 100 lines of code, you can generate what? Like that's 100 by 100 by 10.
Yeah.
Yeah.
And then if you were to actually optimize how the draw calls happen, it would generate a lot faster. And it would run a lot more efficiently. Is this
Yeah.
going to
No,
show?
that's the Discord. Yeah. So that's the thing.
Okay.
So, yeah. I guess those are all the settings, right? Frequency.
Yeah.
Yeah.
Frequency, amplitude, frequency, octaves. And then there's also the cave threshold.
Yeah. Let's see a cave close up.
It's yeah.
It is. It is Minecraft. That's how it's done, isn't it?
Yeah, no, this is just how Minecraft's done.
Proper culling.
There you go.
Yeah, if it had proper culling, it wouldn't run so bad. But yeah, that's Minecraft. Pre-caves and cliffs Minecraft. I don't know what they changed afterwards, but
They did this video on
I
on
saw
the stuff
that.
they had.
Yeah, I was gonna say.
I
yeah, there's a
watched it
video.
like 3 years ago, so I kind of forgot.
Yeah. I can send that in like the resources.
Oh yeah, that would actually be a really good resource.
Oh,
Is it Henrik? Was his
Henrik
name?
Nyberg. Yeah.
Yes. So.
Yes. All right. So yeah, that should be. Is there anything else on presentation? Hold on. Let me check.
I do have my implementation of this exact thing up here. If you want me to bring it up.
Sure.
Yeah. First, let me just double check.
Do I have stream permissions here, or?
You should. Okay. Yeah. That's it. Okay. Yeah. If you wanna come up then.
Whoa.
Back into the OBS.
Is the mic gonna pick me up from back here, or do you want me to come? over
It
here?
sounds like it. It looks like it is.
I'll come over here regardless. I'll